All right, these are AP Chemistry notes, pages 60 and 61. And let's start off with some items for clarity. It says, what is each equation trying to say? So in this first case, we've got a solid on the left, its relative dissolved ions on the right, and a double arrow. So what this is likely trying to say, it's hard to say with certainty without more info, but it's pretty much saying we have a saturated solution at equilibrium. So both reactions are occurring, same rate. So the solid is still dissolving to become ions, and the ions are still solidifying. They're just happening at the same rate. In the second equation, we have an ion here and another ion, and notice the single arrow forming calcium carbonate solid. So in this case, it is showing the formation of a precipitate. So the first scenario with sodium chloride is a equilibrium scenario. The second scenario with calcium and carbonate is not equilibrium, it is the formation of a precipitate. And kind of like I said last time, you might think, well, it'll eventually form a equilibrium system, but that's not the point right now. That happens in the future. This is talking about what's right now. Also, anytime you see something written like this with the solid on the left and the dissolved ions on the right, this is a KSP situation. Whereas the second scenario with calcium carbonate, this would not be a KSP situation. At least you wouldn't use this equation. I mentioned describe a saturated solution using equilibrium. That goes back to the idea of you have a container and you have extra solid stuff. You've got some aqueous stuff. That this can be considered equilibrium because this is happening and this is happening at the same rate. That's what I'm thinking about in that scenario. All right, it's time to deal with the problem of the chart. The chart was for 0.1 molar solutions. And I say it also represents things that are sometimes higher and sometimes lower. Okay, so first let's figure out, when does the chart mean more than 0.1 molarity and when does it not? Well, if something precipitates at 0.1 molarity, it's precipitating because there are too many ions at this concentration. So anything higher than 0.1 will also precipitate. So in this case, if the chart says that something precipitates, it means it will precipitate at 0.1 molarity and higher. If the chart says that something is soluble at 0.1, like rules 1 and 2, that means it'll be soluble at 0.1 and it will be soluble less than 0.1. So like a sodium compound, the chart will say it's soluble at 0.1, but it's also soluble at 0.05. The problem we have, and why I said sometimes the chart is not good enough, is because what about something that precipitates at 0.1? What if you're less than 0.1? Let me move down here a little bit. If something precipitates at 0.1, it means it will precipitate at 0.1 molar and higher, but what about lower? Does it still precipitate at 0.05? Does it still precipitate at 0.01? Does it still precipitate at 0.000001? It might, we can't tell. So we need something to help us with all of these other possibilities. Likewise, even something that is soluble at 0.1, like I said, like sodium compounds with a sodium ion dissolved. That means it dissolves at 0.1, but eventually it won't dissolve anymore. I mean, you can't have something that has a molarity of 10,000 molarity, sodium nitrate, the chart says that sodium nitrate is soluble at 0.1, but that doesn't mean it's insoluble infinitely. This is not possible. You can't get this high. You can't even get anywhere near it. So again, we need something that's going to deal with that. So what the ultimate tool is not the chart. It is comparing the KSP to the current ion concentrations. So that's why this section says precipitate formation. Is it going to precipitate or not? This tool is useful regardless of the chart. It'll either verify the chart is correct, or it will solve those situations where the chart doesn't work. So this is really the proper way to do it, but as you're going to see, it's a lot more work. Now, back last chapter, I went through something called Q, and Q was the products over the reactants. It was just like a equilibrium expression, except it's at an unknown place. And so Q was reaction quotient. What we're going to do is the exact same thing, but I'm giving it a special name. This time I'm calling it IP, which stands for the ion product. And the reason is because our scenario is that we're always going to have a solid on the left, and it will always be in equilibrium with two aqueous ions. Let me actually write it that way. And when you write out the Q expression, there's never a denominator because it would be a solid and wouldn't be in the Q expression. And you always end up multiplying the ions. So it's called the ion product. But it is still the same thing as Q that we did last chapter. All right. If the ion product is greater than the KSP, that means we have more ions than it can hold. So we get a precipitate. And we will keep getting a precipitate until it reaches this scenario in which the ion product equals the KSP, and you now have a saturated solution at equilibrium. If the ion product is less than the KSP, that means you have a lower concentration of ions than is required. So, in this case, you're safe. You haven't reached the limit of saturation yet. So we now have an unsaturated solution, and you could actually add more ions before reaching saturation. So again, this concept of the ion product is the same thing as Q. You can call it Q. In fact, I mentioned the book calls it Q. It is the same idea. And we're always relating it to this scenario that I have here. So again, anytime you're doing an ion product or a KSP, you must do your equation with the solid on the left. I mentioned a note here. KSP is used for low solubility compounds. It's not used with high solubility compounds. So for example, if you were to do a KSP of NaCl, it'd be about 37. The solubility rules can be quantitatively related to KSP, in which the values are greater than 1 correspond to soluble salts. That's just a little detail to be aware of. That's just verifying the chart. So the first calculation, if you look at my work, this is an old problem. I've simplified it. So your notes should say the modified version. So 100 milliliters of strontium nitrate is mixed with so many milliliters of sodium chromate. The resulting solution has an ion product of 5.6 times 10 to the negative 6. Does a precipitate form if the KSP is 4 times 10 to the negative 5. So you can ignore all of this stuff. We will do this in the next problem. I'm skipping just to comparing the ion product, which was given in the problem, 5.6 times 10 to the negative 6, to the KSP, which was given. So that's all we're looking at is what I have in this circle right here. All this other work we'll look at in the next problem. We don't need to do all that busy work twice. All right, the ion product is a 10 to the negative 6. That is a smaller number than the KSP, which is 10 to the negative 5. So no precipitate. If I asked you to describe this solution, you would say that this solution is unsaturated. It's close. I mean, you're not going to be able to get much more. Unsaturated. You wouldn't say it's at equilibrium. It doesn't reach equilibrium until you get saturated, whether you have an extra pile of solid on the bottom or not. So it's unsaturated, not at equilibrium, no precipitate. Now let's go to the big one where we're going to do all this work. In this one, it's the same type of problem, but I'm not providing the ion product this time. Let me only show that stuff right there. Simplify what we're looking at here. Two solutions, a lead 2 nitrate solution and a calcium iodide solution. Will a precipitate form if they are mixed? And the most likely precipitate has a KSP of 8.4 times 10 to the negative 9. I apologize for the messy notes. Yours should be a lot cleaner than mine. So I start out by describing what our system looks like. These two things have already happened before the problem. This is just a way of showing the solution. When lead nitrate dissolves, you get lead plus 2 and you get nitrate. When calcium iodide dissolves, you get calcium and iodide. Now, the question is asking, are we going to get a precipitate from this scenario when these 4 ions are mixed together? Well, you look at your possibilities. One possibility is a combination of calcium and nitrate, but that's not a likely precipitate because nitrate, according to rule number 2, doesn't precipitate easily. But lead and iodide do tend to precipitate easily, and so that's our likely precipitate. So we don't know yet, but if there is a precipitate, it's going to be the lead, the iodide, and they're going to form lead 2 iodide. And make sure that you write your formula correctly, PbI2, based on the charges, and then based on that formula, you have to put a 2 over here in front of the iodide. So that 2 right there, this 2, that 2 is there because of that 2, not because of this 2. That's a coincidence that matched. Now, in order to analyze this, we want to use a KSP style equation. So you should write that out. So this is the equation for a saturated solution at equilibrium. And in this case, you put the solid on the left. This is assuming we do get the precipitate. So again, I still don't know if it's going to precipitate, but if it does, we will eventually end up with this equilibrium saturated solution with lead iodide. It'll be in equilibrium with the lead ion and the iodide ion. So at this point, you might be thinking, why do we write this equation here? And then why do we then write this equation here when they're so similar? It's because this top one is showing the formation of the precipitate, if it happens, And the second one is showing the equilibrium that eventually happens after the precipitate stops precipitating. And this is where we can write a KSP expression, or we can write an ion product expression. So it's good form to do both, even though they might seem redundant. So I mentioned last lesson, anytime you have a volume and a concentration in molarity, you should get moles. We have it twice. So the next step is here is the volume of the lead 2 nitrate. Here's its molarity. So here's the moles of lead nitrate. The ion I'm curious about here is the lead ion, and because lead nitrate gives off 1 lead ion, that's also the molarity of the lead ion. The other solution, here's its volume, here's its molarity, and we get 4.0 times 10 to the negative 3 moles of calcium iodide. But notice, calcium iodide gives off 2 ions of I minus. So the I minus concentration is not 4 times 10 to the negative third. You have to double it. It is 8 times 10 to the negative third. So be careful. And now that is our moles of iodine. All right, I might have said earlier that this up here was the concentration of lead. That's not the concentration, that's the moles of lead plus 2. And here, this is the moles of I minus. You need to be careful there. So now that we know the moles of lead and the moles of iodide, we need to see what their concentration is. So moles divided by liters, but realize we have added these two together. We took a solution that was 0.2 liters and another solution that was 0.5 liters. So our new total volume is 0.7 liters. So I took the moles of lead here, the moles of iodide here, divide by the new volume, and here are my new molarities. This is the molarity of the lead ion and the molarity of the iodine ion. That's what I'm going to plug into my IP expression, which I have over here. So IP is going to be the lead times the I minus squared. And this expression, just like a KSP expression, came from this equation here. The one with the solid on the left and the dissolved ions on the right. Plugged in the numbers. So this one went here. This one here. Do the math. At this point, when you solve for the ion product, this is where we were in the prior question. I had just done all this busy work just so we could compare the two. So now we have an ion product of 3.7 times 10 to the negative 8. We're comparing that to the KSP that was given in the question. By the way, if you're not given the KSP in a problem like this, that means you probably have to look it up in the book. Notice, in this case, our ion product is a bigger number. So yes, it will precipitate. And if I were to ask you to describe what would happen, like it says in the notes, you would say the lead and iodine ions will precipitate until the ion product equals the KSP of 8.4 times 10 to the negative 9, at which point you would have a saturated solution at equilibrium. As it's precipitating, that's not equilibrium yet. That's focusing on the reverse reaction that I have written here, or the forward reaction that I have written here. You can look at it either way. It's only once the ion product equals the KSP that you're at equilibrium. That should take care of it. Let me see what notes I have here. I say in the homework, you will need the KSPs in the book, so be aware. Number 13 has that weird mercury 1 ion. And that should take care of that lesson.